Have you ever really thought about the incredible science hiding in plain sight? In the most ordinary plastic things we use every single day. From a milk jug in your fridge to the bumper on your car, there's this whole hidden world of molecular engineering going on. And today, we're going to pull back the curtain.
Okay, so let's just jump right in with the puzzle. Think about a milk jug. It's got to be flexible, right? You can squeeze it. Now think about a car bumper. That needs to be super rigid to take a hit. Here's the crazy part. They can both be made from the same basic stuff. So how is that even possible? Well, stick with me because the answer is this amazing story of molecular chains, crystals, and a little bit of chaos.
So here's our game plan. We'll start with the plastic blueprint to figure out what these materials really are. Then, we'll dive into a tale of two polymers to see how tiny little changes can make a world of difference. After that, we'll follow the journey from pellet to product. And finally, we'll even take a look at what happens when things go wrong in the factory. All right, to crack our milk jug and car bumper mystery, we have to start at square one. What actually makes a plastic a plastic?
It all comes down to this one word, polymer. The easiest way to think about it is like a chain. It's just one gigantic molecule made by linking up tons and tons of smaller, identical units. And the most common one on the planet is polyethylene. It's literally just a super long chain of repeating ethylene molecules. It's so simple, but that simplicity is exactly what makes it so incredibly useful.
But here's where it gets really interesting. It's not just about the chains, it's about how they're all arranged. See, in a plastic like polyethylene, you've got two things happening at once. You have these semi-crystalline regions, where the chains are packed together super tight and orderly, kind of like neatly stacked uncooked spaghetti. That's where the strength and rigidity comes from. But you also have amorphous regions, where the chains are all just a jumbled, tangled mess, like a bowl of cooked spaghetti. And that's what gives it flexibility and toughness. This balance between order and chaos is absolutely everything.
Okay, so now let's use that idea to solve our puzzle. We're about to see how making tiny tweaks at the molecular level can lead to huge, massive differences in the real world.
So first up, we have low-density polyethylene, or LDPE. Just look at its structure. It's not some nice straight chain. It's got all these branches sticking out all over the place. Think of those branches like little snags or knots on a rope. They just get in the way and physically stop the polymer chains from lining up and packing together neatly. And what's the result? You get way more of that messy, amorphous spaghetti region, which makes the whole material much more flexible.
Now let's look at the flip side, high-density polyethylene, or HDPE. This is such a perfect contrast. Its molecular structure is basically a straight line, almost no branches at all. And without all those bulky side branches getting in the way, the chains can just slide right up next to each other and pack together super densely into those strong, rigid, crystalline regions. And that's what makes the material so much stiffer and stronger.
And these little structural differences have massive real-world results. To really drive this home, let's bring in another popular plastic, polypropylene, or PP. While a rigid milk jug might be HDP, the really tough stuff, like car bumpers, often uses PP because its properties are just on another level. I mean, look at this. Its density is about the same as polyethylene, but its stiffness, it's off the charts in comparison, and it's got a much higher melting point. So that makes it perfect for a car bumper that has to deal with stress and heat, while polyethylene is great for a plastic bag. It's the same exact principle. The molecule's shape determines its job.
So we get the material's blueprint now. But how does it go from a pile of little plastic pellets to a finished product? Well, that's where the magic happens, inside a machine called an extruder.
The whole process is really powerful, but it's also kind of elegant. First, the raw plastic pellets get dumped in from a hopper. Inside, this huge rotating screw grabs them and starts pushing them forward. As they move along, the screw gets tighter, compressing the pellets, while heaters and just intense friction, we call it mechanical shearing, melts them down into this thick, gooey liquid. The screw keeps mixing this molten plastic until it's perfectly consistent, and then it acts like a pump, building up this insane amount of pressure to force it all through a specially shaped opening called a die. And that die is what gives the product its final shape.
And when I say immense pressure, I am not kidding. The pressure inside that machine can easily top 2,000 pounds per square inch. That is the kind of force it takes to wrestle these tough molecular chains into the shapes of the products we use every day. It's this incredible combination of brute force and really fine control, all happening at the same time.
But, this whole process is a really delicate dance. One tiny little mistake in temperature, speed, or pressure can cause some pretty big problems. So, what happens when that perfectly controlled flow isn't so perfect?
Let's think about a specific problem. Just picture that super pressurized molten plastic we were just talking about. What do you think happens if it doesn't flow out of that die in a nice, clean, smooth stream?
Yeah, this is what happens. You get a defect the pros call melt fracture, or my favorite name for it, shark skin. And honestly, that's exactly what it looks like. Instead of getting a smooth, glossy finish, the plastic develops all these little ridges on the surface, which can totally ruin the look and even the strength of the product.
So what causes this? Well, it all boils down to stress. If you try to push the plastic through the die too fast, the surface layers literally can't keep up and they start to tear. Same thing happens if the die is too cold. The plastic kind of sticks and drags against the metal walls, creating that same stress. And of course, the polymer itself matters. Those really long, thick, syrupy polymer chains are just more likely to fracture like this. It's a perfect example of how the material science and the manufacturing process have to work together in perfect harmony.
So we've seen how these simple little molecules can be engineered into this incredible range of materials, designed for everything from flimsy bags to rock-solid car parts. And all of that leaves us with one last really big question. We've spent decades becoming absolute masters at engineering the performance of these materials. How do we now apply that same level of genius to engineering their end of life? That, right there, is the next great challenge.